Okay. Okay, so this question. It's about formulating some kind of logical constraints or whatever. You should probably start with decision variables. Okay, the decision you should make here is which of the programs you want to watch among the programs 1 to 8, in case you've not read the question before. So any suggestion for decision variables?
XP.
Sorry?
XP, whether you're going to watch program P.
Okay, yeah, that is very reasonable. So XP for P from 1 up to 8. And we want this to be a binary one. Is that right? Is that what you were thinking? Yeah. So we want XP to be 1, means watch program P. And we want XP to be 0, which means do not watch program P. So that is hopefully not surprising anymore after all we've been doing. Okay, then there's an objective. So what does it say? Maximize the total joy. Bit of a playful exercise. Pen is not working. There's no meaning to the change in color. The reason is that the black pen is out of ink. Okay, so how would you put the total joy in a formula? Any suggestions? Yeah.
The sum of JP being joy for each program.
JP, XP. P goes from 1 to 8. I think it's quite common for you lot not to state the range of the summation in your formulations.
Could you just do it like for all P existing in P? Is that a better way of doing it?
Yes, you could do, but sometimes people don't write anything, and that's not very good for clarity. So sometimes it is clear what the summation is over, but most of the time it isn't. And then, especially if you're going on to do the code or something, then that creates some problems because then you don't know what to write in Mosul. So it's always good to have something like that. Yes, to your question, George, you could say, I mean, you can't just do JPXP without saying anything. Okay, so you should say that this is JP, because otherwise you're not saying what JP is. And you just couldn't write it like that. Okay, so somewhere you should say that JP is the joy of program P, and let's call this LP. Yes, you could do little p in, say, big P, JP, XP, if you said that P being 1 to 8 is the set of all programs. Something like that. Then yeah, and indeed. You could write it like that. So because the exams are coming soon, for the sake of the exam question, if you've got some, if the question says JP is the joy of P or something like that, you don't necessarily have to repeat it in your answer. can do for completeness sake. We don't necessarily have to. But if it doesn't, like in this example, it doesn't say what JP would be. Then you should say what you mean by JP somewhere. You know, like a remark, JP is the joy of program P, something like that. Because otherwise it's not defined, it just comes out of the air. And, okay, and what are the constraints? Okay, so the first thing that you see is that you must not watch TV for more than 2.5 hours. So that would be, how would you write it?
Sum of all LP XP so less than equal to 150 over all P.
Yeah, 2.5 hours is indeed 150 minutes. So if your L's are in minutes, 150 is not going to say. So then you can watch no more than one of 1, 2, and 3. Kind of obvious. And no more than one of 6 and 7. Well, that's also obvious. So x6 plus x7 only more than 1. And then finally, you don't want to watch 6 unless you also watch 4. Sorry. How does that turn into a linear constraint?
Do x4 is greater than or equal to x6.
Yeah, something like that. So x4 one way or another. So this prohibits x4 being 0 and x6 being 1, which is exactly what this says. Okay, is that clear? And then, anything missing? What's missing? That's part of the constraints. I mean, you're stating it kind of here, but that's more like the interpretation of what it is than a constraint. So you should always put it in among your constraints as well. That's it. Any questions? Yeah.
Will you lose marks for not putting that bottom line in an exam?
I don't know. I'll fill it. I'm going away, so I'm not going to be marking. So when I was marking these exams, don't know, if everything else was correct, then you probably lose 1 mark or something like that. But if there were some other errors, then, you know, like if you want full marks, then probably it wants to be fully correct. But then it kind of counts like -1/2 or something. If there's some tiny little bit missing elsewhere, then So definitely, if you don't put even this here and you don't put this here, then you're not like this interpretation, and you're not putting this binary here. Then certainly that's a mistake, because you're nowhere saying that these should only be zeros and ones. Well, if you put this here, or you write here all binary variables when describing them as decision variables, then I'm a bit more tolerant of you not repeating the same thing at the bottom. But again, that's the thing that's passed. Okay. Any other questions? No? Good. So let's do exam question 7 from last year. Have a quick look at it. Read through before we start trying to solve it together. Okay, so what do you think? Hard or easy? But obviously you've not really been preparing yet very much. So
It's hard. I can't remember any of this.
not even part B.
It's big.
It's been an assignment. Well, similar to an assignment. Okay. Okay, so one thing you want to be able to do is solve integer programs by branch and bound. Even if you can't do the top bit, it gives you 14, which is 70%. And then you can have a go at part A, which is actually not very hard. And it's a proof that we did in the lecture, and it's a proof that is in the booklet. Yeah. And you've probably forgotten by now. But it isn't very hard to do. So you want to prove that Cx is less than or equal to B transpose Y if X is feasible and Y is feasible. So what does it mean to be feasible? It means it satisfies these constraints. Okay. For X. So this one and that one. So when you're looking at C, it appears here, and you kind of, well, if you have CT is less than or equal to ATY, you can take the transpose of this equation, which gives you C is less than or equal to Y transposed A. So it really is just kind of manipulating vectors and matrices, but you probably need to remember how, or try and find out on the spot. It's not very hard. So when you've got this, what you can do is you can get Cx. Now, Cx is less than or equal to y transposed Ax. So this is like, yeah. This is like, so C less than, this is actually a system of equations because C is a vector and y transposed A is also a vector. And what you're doing using this X is you're taking like a linear combination of those inequalities and adding them together. So you can do this, it doesn't destroy the less than or equal to because X is greater than or equal to 0. Okay, so it kind of means like each of those inequalities you multiply by a non-negative number and then you add them all together and you still get an inequality that works. So you've got this, and that's a good thing to have. And now you know that AX is less than or equal to B because X is feasible. And so by the same trick, you can do this because y or y transpose is greater than or equal to 0. So that's the same thing, okay? AX is less than or equal to B is a system of linear inequalities. There are as many as there are rows in the matrix A. And if you take some non-negative coefficients, it's like each of those inequalities you times by a non-negative number, and then you add them all together, and that's what you get. It really is more or less just an exercise in vector and matrix multiplication, for which somebody else is responsible, and you should know. Okay, so now if you take this first one we got and the second one we got, they imply that Cx is less than or equal to y transpose B. But that's not what we want to do, is it? It asked for B transpose Y, and we got Y transpose B. Is that a problem? So C is a row n vector, and X is a column n vector. So what is C times X? Is that a matrix? Is that a vector? No, it's just 1 by 1, because C has one row and X has one column. So when you times them, you get a 1 by 1 matrix, as it were, which is just a number. And same for here. So this is just a number. So if you have one real number, or like look at it as a 1 by 1 matrix of a sort, you can transpose it, and what you get is exactly what you have because there's nothing to transpose. Okay. So that's everything. End of proof. Okay, I know it's a bit unexpected that you have to deal with this now, and not everybody is perhaps ready, but anything that needs a clarification on the answer? Or does it make any sense at all? Shall I go into more detail? Or is that, there's nothing deep going on, really. It's just you've got a couple of inequalities that you need to combine in the right way to get what you want. So there isn't much to understand about it. You just need to kind of remember how they're put together as a puzzle, so you get what you want. Okay, shall we move on then? Part B. So how does branch and bound work? Anybody remember who's been doing the assignment? Yes, George?
You find the optimal solution first that uses decimal points, and then you find different possible routes that are either rounding up or rounding down, but the individual decision variables to find which one's optimal.
Yeah, that's quite a good general description. So one thing you need to be able to do if you want to answer like 5 questions in 3 hours is you should be able to write a Mosul code that solves that LP in like 5 minutes, which is definitely possible. Because it's it looks like this. Okay, so you can sort of ignore that part. Okay, this is not necessary. But the rest is absolutely straightforward. Yeah, just look at the variables. Okay, there are 3 decision variables: x1, x2, x3. There are these 3 constraints. Okay, 1, 2, 3. Non-negativity you don't have to write. That's automatic. And the objective is that, and that's everything. Okay. This thing is there just to tell you when you get an infeasible problem. If you don't put it in, because it's kind of hard to remember all these things, if you don't put it in, you just have to check, you know, when Mosul comes up with the solution that it's actually satisfies all the constraints, or when you go to stats on the right, click stat, statistics, or whatever it says, that it says LP optimal and not infeasible. Otherwise, you'd be interviewed. Okay? But the actual constraints, very simple. So, I do it, it gives me this solution. The objective, ignoring the constraint that it should be integral, I get 83.79. X1 is 3.82. X2 is 0, and X3 I get 6.58. So I start my branching tree. Okay, this is my problem S. These are the values. And Z is 83.79. And now I want to branch. Keep a list of unsolved problems. So how do you want to branch?
Branch on X3.
Branch on X3. Is that what I did? Doesn't really matter. So what are the two branches? X3 should be
Less than or equal to 6 or greater than equal to 7.
exactly. So that creates problems. Oh no, I'll call them S1, S2. So now I have unsolved problems S1 and S2. Now I pick one of them and solve it. Anybody have a particular preference which one to solve first? No? Okay, so let's go and solve S1. So what does that mean? I go back to my modal. The constraint I want to add is that X1 is less than or equal to 6, so I can just add it here. X1 is less than or equal to 6. And solve again. So if I do that, what? No, X1, X3. Sorry. What? X3 is less than or equal to 6. So I noticed because it was giving me the same solution as before. So when I solve it with X3 is less than or equal to 6, that's already solved. I get Z equal to 83.5 and X1 3.82. And X2 is 0.86 or something, and X3 I'm getting 6. Because I want to branch again. What do we pick? X1 or X2? X1? Okay. So I get X1 is less than or equal to 3. X2 is greater than or X1 is greater than or equal to 4. Okay? And I've got S3 and S4 is still unsolved. So do I want to solve S2 now? No.
Which is to do S3.
Okay, let's do S3 then. Fair enough. So S3, I get X1 is less than or equal to 3 as a new constraint. So I just added on the other one. 3 is less than or equal to 6. I get Z is 82. And X1 is 3, and X2 is 1, and X3 is 6. Okay, that's all integer, so no more branching. Make a note. And integer. No more unsolved problems. Add it, but we still have 2. So which one do you want now? It's 4. Okay, let's do this 4. What is it? X1 is greater than or equal to 4. So I get Z equal 81.5, and I'm not really interested in this, am I? 4, 0.5, and 6. Do I want to branch? No? Why not? Yeah, I didn't note it down, but the incumbent I found now is 82. Okay. Well, 82 is better than 81.5, so this is proven suboptimal. It goes away. There's only one left now. I need to make x3 greater than or equal to 7. I get 0, 0, 7. And Z in this case is kind of easy. 0, 0, 7, so it must be 77. So that's S2 solved. Any branching? No. Because it's both integer and suboptimal. No more unsolved problems. So the optimal solution is the best one we've found so far, and that was 82. So x1 is 3, x2 is 1, x3 is 6, and the objective is 82. Problem solved. To what? To what?
And we always have to start on the left.
You mean like which problem you pick next? No. But, George, you suggested something when I was asking, what do we go for now? S2, S3, S4? You said S3, not S2.
Yeah.
Did you have any particular reason for
When you first told us, you said you should just go down one branch and then start trying to do everything else after that.
Yeah, I probably didn't mention that. Well, yes. I mean, it's a bit of a hit and miss. I mean, there's solving integer programs is hard in the sense that if you're making bigger and bigger ones, there are no good algorithms known to do it really fast. And the complexity really comes because every time you kind of double the number of problems you have. So yeah, so it grows very quickly the number of subproblems you have to solve. What George is mentioning is that when you're making solvers, they usually what they will do is try and go down one branch. So always go down and down and down first until you find an integer solution. Because if you don't have any integer solution at all, then you can't do pruning by suboptimality at all. Right? So it's kind of good to have an integer solution quickly because then you're hoping that many of those branches you won't have to go down because they will be suboptimal. And that's a good kind of approach, especially for bigger problems. So with small problems, it's a bit of a question of getting lucky and not having to go very far down. But the problems I put on the exam, I mean, like this one tends to be, well, they tend to be like, if you look at this one, there's not much that you can do wrong. Okay, so if at the beginning you chose S2, you'd be very happy because then you found an integer solution very quickly. If instead of going that way, you went that way, well, then you have to branch, and maybe you take a bit longer to get there. But you don't know in advance what's going to work or not going to. It's just no way of knowing. What I would say for the exam is if you're solving, if you've already got like 10 problems or something, then look back at it and say, okay, that's not the right thing because problems I pick for the exams should be solvable in one the problems, just because the idea is to test, you know, the method and not you can do lots and lots of computations. Yeah. Any other questions? Yes.
Can you show us the modes of express and express?
Oh. Yeah. But you also have it in other places, like the booklet or the model solution, and so on. You don't have to write it down now or remember it at this moment. But yeah, there's this function which returns information about what it found the problem to be, whether it's found an optimal solution and returns this, or it's infeasible, or unbounded. But well, obviously you won't get this problem. Obviously is not unbounded, so I'm not even testing for that. Everything. So I think we agreed with Philip that I will have both lectures next week, and we can do the remaining 2 questions in the handout. Because then in the final week of term, I'm no longer here. And then good luck. So, yeah, that's it for today.